Hello everyone, welcome to the Spintangle. Today, this is a special lecture on Ising model. Okay, this Ising model is an approach of study the thermodynamic properties of a magnetic system. Okay, or you can call that whenever external magnetic field is applied to a system, therefore to study the entropy or the temperature is done by Ising model. Okay, this is a very interesting model. Okay, so let's start the definition. What is the definition of Ising model? Okay, I'll be moving on to this diagram. Okay, I'll be moving on to this diagram. First, let's write the definition of the Ising model. Okay, let's write the Ising model. The Ising is capital I because this is the scientist who invented this Ising model. Okay, this is a theoretical model. The Ising model is a mathematical model that doesn't correspond to actual physical system. Actual physical system. Okay, say it is a theoretical model of studying phase transition properties in the systems where magnetic field is applied. This is the definition. Okay, my handwriting is not too much not too much good, so please make an adjustment on this. So this is one of the few exactly solvable models where we can actually compute thermodynamic quantities and interpret them. Okay, this is one of them. Okay, so let's take what entropy is. I am moving on to the fact that what entropy stands for. This is a completely theoretical class. Entropy stands for the degree of disorderness. Okay, the degree of disorderedness. This is what you call entropy. This means, say you have a system in which the particles are arranged like this. Just consider them as particle. Okay, these are I will be treating these as individual spins, but I am not moving onto the fact that these are the individual spins. Okay, I am just considering that these are the particles which are arranged in one dimension. These are one dimension. The model this model is proposed by Robert Ising. I think so. This Robert Ising in 1925. I think so. 1925, 1925. And he calculated the theoretical one-dimensional Ising model in which he had arranged particles in a row and calculated their thermodynamic properties like entropy, mainly entropy and temperature properties. Okay, this is the target of Ising model. So say these particles are arranged like this, and if you look at another system, this is, say, this is system 1 and this is system 2. So in the second system, say these are, I think these are 7. Okay, these are 7 particles. Okay, these are 7 particles in which I am making one particle flip toward downward. Okay, one particle flipped toward downward. If this particle flipped toward downward, the Ising has treated this thing as ordered, because you can easily check this thing that this is ordered state. Okay, this is ordered, and this, and the second system, and our second system is so called disordered. Why this is all, this looks like disordered. Okay, why this is disordered? Because you have one indisciplined particle. This particle is flipped downward. So Ising suggested that this particle will affect its instant neighborhoods. Okay, affect these instant neighborhoods by raising the entropy. Okay, so you can easily check this thing that if this is the one particle which has been flipped towards down, okay, and this will cause this particle, these two instant neighborhood particles to behave in more disordered manner. This means, therefore, here it is a disordered system, disordered place in a system. I can say this is disorderedness. Okay, this is what he called. So in case of entropy, say the entropy of this thing is written as S1, as the entropy of this thing is S2. You can easily check this thing. The entropy of this thing is low. The system 1 has entropy lower and the system 2 has entropy higher, because the system 2 is more disordered than system 1. So if entropy increases, then the temperature will also increase, and in this case the temperature will be decreased. And we know, if the magnetic field, you can check this thing, that the magnetization, I am writing the magnetization is increased in this thing, because the temperature, this is thermal agitation called, this is the thermal agitation. This is the thermal agitation, and this thermal agitation causes the magnetization to become higher, because thermal agitation low means the particles, say these particles are randomly scattered in very special directions. So the magnetization will be possible only if they are aligned, because you can check this thing by a vice versa method. You can check this thing. If you apply magnetic field to a domain, you can say this is a domain. I think if this thing, this is a system, and say these are the two domains in which the particle are initially randomly scattered, and in the second domain you have this thing. Okay, whenever you apply magnetic field on this, here magnetic field is off. Okay, so the particles are, these are the domains are randomly scattered, and whenever you switch on the magnetic field, the domain got aligned. Okay, say this is the system and the domain got aligned, okay, in a particular direction, say in this direction, these domains. Okay, the domains got aligned. This means the domains responded to the magnetic field and they got aligned. Therefore there is, if there is thermal agitation, therefore you can easily check this thing, that the domain will not be aligned perfectly. The domain will try to become disordered from its mean place. Say this domain will be like a I think like a stick, you can easily check this thing, that whenever you boil or heat up some, say you have water on a glass, okay, you are not giving heat on this. When you are not giving heat on this, the particles remains in the equilibrium place, and whenever you are giving heat, okay, whenever you are giving heat to this, the particle will will become displaced. This is because of the thermal agitation, okay. So the domain also got try to got displaced by applying external heat, okay. So therefore, if the temperature is lower, the domains try to arrange like more stable format, okay. In the more stable manner they will be arranged if the temperature is low. If the temperature is very high, the thermal agitation will be very high and the magnetization will be low, because these domains will be try to deflect from this position, okay, will try to deflect from this position, and they will make a two-dimensional angle here, two-dimensional angle. So is a low temperature this is a low temperature condition in which the magnetization will be possible the most, okay. So now I am moving to the second system. So this is the first system, and the second system will be what? Second system is disordered, because this is the observation of Ising, not observation. This is the theoretical hypothesis of Ising, Robert Ising. I think name is Robert Ising. Check this thing, Robert Ising. I have forgotten this thing. His name is Robert Ising. Robert Ising suggested that whenever there is a disorder, the more disorder will be filled by the neighborhood. Okay, say you have a house here, and say these are the two neighborhood, okay, of yours. If your house got burnt out, okay, your house got burnt out, therefore who will feel the burning pain? Your instant neighborhood will feel the burning pain, okay, the most. This is the model of Robert Ising. So I am moving to a diagram which I have drawn on the very initial. Say this is the two-dimensional case. This is the two-dimensional case in which you can easily check this thing. This all domain should arrange like a pro, okay, should arrange like they are aligned in a particular direction. The magnetic field is in this direction, so the domain got aligned in this direction. This is a ferromagnetic domain, you can call it, okay. Whenever there is a problem, say this is all the domain are aligned in a particular direction, but this domain does not. This will flip in the downward direction. So what will cause here? It will cause its instant neighborhoods. Who are the instant neighborhoods? Say these are the instant neighborhoods. These are the instant neighborhoods will be affected the most, and this will create a disordered situation in this domain, okay, inside this thing. So this is the two-dimensional Ising model, and you can check this thing in the three-dimensional Ising model. There are several pictures in Google. You can check this thing, that you have a disorder state here. Say this is the disorder. You have a disorder state here. So that will be affected. That will be felt by the most of its instant neighborhoods. Okay, this is the theory of Ising model. Okay, so now I am moving to the spin model of the Ising model, like a spin concept of the Ising model. Let's write. Spin concept of, you can write this thing, spin concept of Ising model. Ising model, basically Ising model does, what does the Ising model? That Ising is the study of, it is the study of interacting spins. It is the study of interacting spins. Okay, so let's check. Let's check this thing. Okay, say let's discuss with the problem format, in which what you have to do. The problem format will be what? First of all, what you have to do? There are two types of problems. Okay, two types of problems which are basically asked. Two types of problems, in which the first type, you will be given the structural combination. Structural combination, that means a geometrical shape you will be given, a geometrical configuration. Okay, this is geometrical. And in the second type, there will be no structural combination, Hamiltonian given directly. Hamiltonian given, there is a no structural combination. So let's move on to the structural combination method. Okay, in structural combination, say you will be given, I am writing this thing, let's make a heading first. If structural combination is given to you, okay, therefore what, this will be a elaborate discussion, so be patient. Okay, structural combination. First of all, what is structural combination? Structural combination means, say you have given, say, three spins are connected in a line. Okay, this is the structural combination. Say the structure will be what? Say three spins, you have one spin here, one spin here, another spin here. This is a line. Okay, or you could have been given that three spins are connected in the vertices of a triangle. Okay, on a triangle. So what will be the structure? Say this is a spin, say this is a spin, say this is a spin. Okay, this is the thing. And or you could have been given that three spins, 3 4 5 6 2 1 2. There could be any number of spins. Okay, three spins are connected in equidistance over a circle's perimeter. Okay, circle's perimeter, like this. I am drawing this thing. So you have a circle here. So you have a circle here, and the three spins are like this thing. These are the three spins. Okay, these are the three spins. Or you could have been given any kind of structures. So first, what you have to do in the step 1, I am writing the step 1 as the step 1, you have to construct the Hamiltonian. Okay, you have to construct this Hamiltonian. What is the formula of Hamiltonian here? Hamiltonian formula is somewhat written as, say it is written as, let me check this thing first. There are several kind of symbols. What could be written here? Say the Hamiltonian is written as H equals to summation I comma j. Okay, I comma j. This is capital J I j. Okay, capital, there is a minus sign here, and sigma I sigma j, and here it is a, say, small h sigma j. Here is a j. This is the general format of Hamiltonian. Okay, I'm writing this thing, just wait for a while, where j represents jij represents the spin interaction, spin interaction. And what H represents? H represents the, let's write this thing as B. Okay. Let's write this thing as B, not H. Why B? This is the external magnetic field applied. Okay, external magnetic field applied. This is the format of the Hamiltonian. Okay, so what do we have to do in the step 2? I'm writing step 2. First of all, let me write the step 1, step 2, step 3, step 4, and whatever it is, and therefore we'll be taking a example. Okay, step 2. What is our step 2? Step 2, make a table, make a table consisting all possible combination of spin and calculate respective energies. Okay, this is the step 2, in which you have to put this thing, say this is, here is, you have to put the sigma i's here, sigma j's here. Okay, and therefore you have to calculate the energies. Okay, from the Hamiltonian, you have to calculate energies. This is the table. The third step will be what? Step 3. I think it is making another table. Making of another table of energy versus degeneracy. Energy versus degeneracy. What this thing we used to do in case of partition function finding. Okay, so this will be say energy here, and its degeneracy will be here. I think you know this thing from the partition function calculating process. So this is the pre-process of finding the partition function. So you have to find in the step 4. In the step 4, you have to find the partition function. This is our final target. Okay, step 4 will be what? Find partition function. What is our partition function? Partition function is written as, say, single particle partition function is written as gi summation gi a to the power minus beta ei. I think you know this thing. Okay, and therefore up this thing is okay. You have to remember these 4 steps. If you calculate it, I am writing this thing, if you calculate partition function, then you will be able to find other thermodynamic parameters. Okay, after this, these are the 4 steps you have to remember in case of solving Ising model problems. Okay, so it is very much important for CSIR NET, GATE, or IIT JAM, Tifr, or any other purpose. Okay, so how to write the Hamiltonian and how to calculate these all things. Okay, so let's start with some standard problems. Let's take some standard problems. Okay, say this is, I'm not giving question, this is example 1. So you have n equal to 2 spins connected as a diatomic molecule. Calculate the partition function. Calculate the partition function. So this is our question. Now, what you have to do in this case? These are the examples, not the actual problems. Okay. Just wait. Say they can be arranged like this. Say this is one spin. Say this is spin 1. This is another spin, spin 2, and okay, that can be arranged like this. Okay, that can be arranged like this. Whatever it is, in each and every case. First of all, what you have to do, you have to step 1. You have to what was our step 1? Step 1, write down the Hamiltonian. Hamiltonian is what? Hamiltonian is equals to summation I comma j. Just wait. I am quite dyslexic. J I j sigma I sigma j minus summation of b sigma j at the summation over j. This is our Hamiltonian formula. There is a minus in it. There is a minus in it. So in this case, what you have to do? First of all, there are 2 spins, S1 and S2. So I will be what? I will be 1 and 2. So let's put this thing. This will be j minus j 1 2. I is 1, j is 2, 1 2, and there will be a say this is sigma 1 and this is sigma 2 minus there is a b. You can take this b out from the summation symbol because b is constant magnetic field. Okay, so b, and what is our sigma j? Sigma j is will be sigma j is because we have two particles here, so sigma j will be s sigma 1 plus sigma 2. This is the Hamiltonian, and now you have given, if you have given say s equals to half and s2 equals to half, put them on this formula. Okay, and you will be giving your answer. I'm not doing this thing, I'm doing just these steps. Okay, this is example 1. Now move on to the example 2. What is our example 2? Example 2, say you have given n equals to 3 spins. Okay, n equals to 3 spins. In case of n equals to 3 spins, the spins are, there can be two type of combinations. The spins are placed in a row. This is our most important example. Okay, most, not most, is more important. Okay, so you have given n equals to 3 spins. These spins are placed in a row. This is one combination. Say this is example 2a. This 3 spins can be arranged like a row. This is how it look like. Say this is one spin, this is spin 2, this is spin 3, s1, s2, not writing s1, s2, sigma 1, sigma 2. Okay, say this is sigma 1, sigma 2, sigma 3. What is that in this case? Change this thing, s1, s2. Okay, this will be sigma 1 and this will be sigma 2. So sigma 1, sigma 2. What is our sigma 1, sigma 2? And therefore write down the Hamiltonian. Hamiltonian is what? Minus summation of j ij sigma I sigma j minus b sigma j. Okay, so what does it become in this case? Minus, you have 3 spins. You have 3 spins. In 3 spins, what you can calculate? First, considering the interaction between, say there is a change, say there is a flip out of the spin, so these will be affected the most because this is the instant neighborhood. Okay, so the Hamiltonian will be what? The Hamiltonian will be minus j 1 to sigma 1 sigma 2 for the first pair, and now I'm moving to the second pair. Say this is and this is, so what will be there? J 2 3 sigma 2 sigma 3, sigma 2 sigma 3. Okay, and minus there will be a 0. I'm moving to the fact, I am moving to, just wait, I'm writing this thing, 0 sigma. Now moving to this thing, that these two terms, that sigma 3 and sigma 1 term, this is quite interesting to write. 0 times sigma 3 and sigma 1, and the b is like this. B, there are 3 spins, so there will be sigma 1 plus sigma 2 plus sigma 3 terms. Just wait for a while. Why I have been written this 0 here? Because you can easily check this thing, that this is your sigma 1, this is your sigma 2, this is your sigma 3. Okay, the instant neighborhood of sigma 2 is what? sigma 1, because therefore there will be an interaction term j12. Okay, j12 has some certain value. Okay, and the instant neighborhood of sigma 2 is what? Sigma 3. So sigma 2 and 3, j2 and 3 will also be valid. But in case of sigma 3 and 1, which I have written 0. Why 0? Because the instant neighborhood of sigma 3 is not sigma 1. They are far away from each other. So there we can treat that j31 as 0. Okay. In case of Ising model, what I have said in the very early of this lecture, that Robert Ising calculated this thing for your instant neighborhood, not the far neighborhood. Okay, not the far neighborhood. You have to calculate the disorderedness related to your instant neighborhoods. You are disordered, so this disorderedness will be distributed among your instant neighborhoods, not your far neighborhoods. Okay, so this is the condition why I have written this term as 0. Okay, now this is the example 2a. I am moving on to the example 2b. What is our b? B is, say you have 3 spins, n equals to 3 spins, which are arranged like this. So you have in the vertices, on the vertices of a triangle. Okay, this is a triangle in which these are the vertices. N is equals to 3 spins. Okay, so what you have to do here, in case of, you can easily check this thing. Say this is sigma 1, this is sigma 2, this is sigma 3. Now write down the Hamiltonian. The Hamiltonian will be what? Hamiltonian is given as minus jij sigma I sigma j minus b summation of sigma j over j. Okay, this is not sigma j over actual j. Actually, this will be all of the particles. Okay. So here I can easily write. Let's take this interaction. Let's take the first interaction. Okay, this interaction is 1 and 2. 1 and 2. Okay, these are the instant neighborhoods of each other. So I can write this thing minus j12 sigma 1 sigma 2. Now I am considering the sigma 2 sigma 3 interaction. Okay, this is a equilateral triangle. Okay, this is a equilateral triangle. This will be minus sigma 2 j23 sigma 2 sigma 3. And now considering the sigma 3 sigma 1 term, that too I have omitted on the previous example of example 2a part. Okay, that the 3 and 1 are not related to each other. In this case, the 3 will be instant neighborhood of 1 also. Therefore, there will be another extra term, non-zero term, non-vanishing term, that is sigma 3 1 j3 j3 1 sigma 3 sigma 1, and by decomposing this thing, you can easily write this thing as sigma 1 plus sigma 2 plus sigma 3. This is all. This is the Hamiltonian. First of all, learn to write the Hamiltonian properly. Okay, this is the most important part of this equation. Okay, this is the example 2. I think example 2 is over. Let's move on to the, just wait for a while. Let me check this thing. Example 3. Example 3 is what? N equals to 3 spins symmetrically placed on circumference of a circle. n equals to 3 spins symmetrically placed on circumference of a circle. So what you have to do here, so we have circumference right now, just wait, let me change the ink first. Say you have a circle. In this circle you have 3 spins. This is spin 1, say this is sigma 1, and here it is sigma 2, here it is sigma 3. So writing down the Hamiltonian here, also you can check this thing. The Hamiltonian will be what? The Hamiltonian will be just wait for this. Hamiltonian is given by minus summation ij jij sigma I sigma j minus b sigma j. This is, here is j. So you can easily check this thing, that considering the interaction between this spin and this spin, okay, these are the instant neighborhood from each other, okay, instant neighborhood. So what will be here? So minus j1 2 sigma 1 sigma 2 minus j 2 3, considering these two interaction 2 and 3, okay, j 2 3 sigma 2 sigma 3, and this will be considered because sigma 3 and sigma 1 are also there in instant neighborhood. So there will be a j3 1, there is a sigma 3 sigma 1, and here will be another term, say minus the magnetic field, the magnetic interaction term, that is b. There are 3 spins, so sigma 1 sigma 2, that's sigma 3. Okay, so this is the Hamiltonian that you could have been given some kind of shapes, and you will be asked to determine the Hamiltonian of the system, and you have to calculate the Hamiltonian, and therefore the energies, and therefore the tabulation, and therefore the partition function, and therefore other parameters. Okay, so this is a long process, but you have to calculate. These are not too much critical process to solve this thing. Okay, now I am moving to a very interesting problem, that is say four spin. If there are 4 spin given, okay, 4 spin, this is the most interesting case. Example 4. If you have n equals to 4 spins given, if you have n equals to 4 spins given, therefore system of 4 spins, you can, the 4 spins can be arranged like, say I am giving arranged, these 4 spins are arranged in a line. Okay. So what will be the line? If it is line, calculating the Hamiltonian first. This is 1 spin, this is 1 spin, this is 1 spin, this is 1 spin. So what is this? This is sigma 1, sigma 2, sigma 3, sigma 4. So calculate the Hamiltonian. What is our Hamiltonian? Just wait 1 second. What is our Hamiltonian? I think you can now calculate the Hamiltonian. Minus summation over ij. There will be a jij term, this interacting term of the spin interaction. Okay, there will be sigma I, sigma j minus b. There it is a summation over, there is a sigma j. Okay, this is the Hamiltonian. And now calculate the interacting term. First, take the interaction between sigma 1 and sigma 2. There will be another term, say sigma 1 to j1 to sigma 1 sigma 2 minus, considering the sigma 2 sigma 3 interaction, there will be a sigma j2 3 sigma 2 sigma 3 minus the start terms with 3/4 interaction, there will be a sigma 3 j3 4 sigma 3 sigma 4, and we will calculate the interaction between the sigma 4 and sigma 1 will be what? Zero term. Okay, I am writing this 0 directly, not writing anything. This is sigma 1 0 times sigma 1 sigma 4, and the magnetic field term will be when it's b, there is a sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. This is all. Here I'm not writing this thing that this is not allowed. Okay, I am writing this thing that this is the 4 and the 1 are not their instant neighborhood, because therefore the interacting term, say j41 will be equal to 0. Okay, because the Ising model is completely based on instant neighborhood properties. Okay, this is the four spins arranged in a line. So now I'm taking the second part of this thing. What is our second part? It's a B part, arranged in a 4 spins. Okay, arranged in a circle, in a circumference, symmetrically. Okay, arranged in a circumference symmetrically. So in the previous lecture, what in the previous section, what do we have discussed like this thing? Say this is our arrangement. Say this is the circle, and take some other color. So if this is 12 a.m. position, this is 3 a.m. position, 3 p.m. position, 6 p.m. position, and 9 p.m. position. These are the 4 positions in which the spins, say sigma 1, sigma 2, sigma 3, and sigma 4 particles are placed. Okay, so calculate the Hamiltonian here. I think you are now expert in calculating the Hamiltonian. Okay, what is our Hamiltonian? Just wait 1 second. What is our Hamiltonian? Hamiltonian is given as minus j ij. There is a ij term. This is I. This is j ij. Sigma I, sigma j minus b, sigma j. Okay, now what we have to calculate from this thing, considering the interaction between sigma 1 and sigma 2. So what there are instant neighborhood, so plus minus sigma j1 to sigma 1 sigma 2, and for sigma 2 3 there will be a minus j2 3 sigma 2 sigma 3, and then for sigma 3 4 there will be a minus j3 4 sigma 3 sigma 4 minus, here is a sigma j. This is also allowed because the instant neighborhood of 4 there is 1. Okay, therefore j 4 1 sigma 4 sigma 1. Okay, and magnetic field terms, so b sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, this is all. And the very last part of this lecture, this is the C, that is the spins are arranged in the corner of a, say it is square, if there is corner of a square. So in case of this is one of the most important example of this thing. Okay, this is one of the most example. There will be two external terms. Okay. Let's take a square. Say this is a square. In this square you are supposed to place 4 spins. Say this is sigma 1, this is sigma 2, this is sigma 3, this is sigma 4. Okay, so writing down the Hamiltonian, what will be our Hamiltonian? Our Hamiltonian will be minus, I am writing summation over j ij. Write each and every term the Hamiltonian formula, so you will be able to remember this formula. Okay, jij sigma I sigma j minus b sigma j. There is a j term here, ij. So what will be here? Considering the interaction between the 1 and 2 interaction, 1 and 2 interaction will be minus j12 sigma 1 sigma 2 minus, this is sigma 2 and sigma 3 will be what? Minus j23 sigma 2 and sigma 3 minus sigma 3 and sigma 4 will be what? j34 sigma 3 and sigma 4, and the very last minus j41 sigma 4 and sigma 1, and there will be external two terms that are non-interacting. Why these are non-interacting terms? That let me take the interaction between these two terms also. They are not instant neighborhoods, these two terms. Okay, interaction of sigma 1 sigma 2 sigma 3, and also between the interaction of these two. Why I am taking this? Because you are calculating the Hamiltonian in a very small place, and in a very small place these two interaction terms will be non-zero. Okay, because they are not too distant from each other. Say this is the distance a. So what is the distance of this thing? This is, I think what is the distance? Say a times a root over root 2a, I think so. This will be, the distance will be root 2a. Okay, this is not too much higher. This is not too much higher than a. So sigma 1 and sigma 3 and sigma 2 and sigma 4 interaction will also be calculated. There will be another term which are called j13 sigma 1 sigma 3, j24 sigma 2 sigma 4, and the magnetic field terms, say minus b sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. Okay, now the question arises, the value of j12 j23, will it be same with the j13 j24? These are the higher interacting term. Okay, these are higher interacting term. Write this thing. j12 will be, I think, will be equal to, if the spin are same, therefore j12 will be equal to j23 equal to j34 equal to j41. Say, and these are high, these are quite high. I am writing these are quite high, quite higher than j13 equal to j24. Okay, because these are the direct interacting terms and these are the cross interacting terms. Okay, this is all. The lecture of Ising model is over now. So thank you for being with us, and share among your friends, subscribe the channel and hit the like button. Thank you.